Good afternoon, sir.
All right, we will wait for 1 or 2 minutes, then we'll start the class. Okay. Is my screen visible?
Yes, sir.
Okay, so let us start today's class. We will discuss today about deadlocks. Um, Let us recollect before talking about deadlocks what we discussed in the previous class. In the previous class, we started discussing operating systems, process management, CPU scheduling algorithms. Then in the previous class, we discussed process synchronization. Uh, because of race conditions, uh, the yield, the result what we get sometimes may not be correct. So we need to make sure that processes are synchronized when it is executed in a multi-programming environment. So we studied two important methods to synchronize the process, and we try to understand critical section problem. That critical section can be implemented using mutex locks or semaphores that we tried to study and understand in the previous class. Now let us understand one more important aspect of operating systems called deadlock. Usually what happens is in a multi-programming environment, there are several processes. uh, Even a process can be classified into multiple parallel execution. It will act as a threads which are independent from each other. They will keep executing, and um, so you can say that in a multi-programming environment, several threads may compete for finite number of resources. This multi-threading programming you can also observe in Java, uh, where you can execute part of a section, and Java supports multi-programming. Similarly, as a processor can also execute multiple programs. We call that each program as a thread, the independent part, where it will not depend on the other part of the program. Uh, these programs can be categorized into several threads. Each thread, when they are executing, they will compete. They will come into competition to utilize some resources. These resources, what we have, are finite. We don't have infinite number of resources, so we have finite number of resources. So with that available finite number of resources only, we need to allocate to the threads to complete their job. If the job is not completed, then the process will not complete, right? So as a thread requests resources, if the resources are not available at the time, then the thread will go into a waiting state. If Sometimes a waiting thread will never again change its state because resources it has requested are held by some other waiting threads. Okay, this situation is called deadlock. For example, I will show you one diagram which will make even more clear sense. So deadlock as a situation in which every process is a set of processes is waiting for an event that can be caused only by other process in the set. For example, let us see that. Let us assume T1, T2, T3. You can consider them as a threads or you can consider them as a processes. Either way, deadlock may happen. Even the same logic will apply to the process also. You can assume that P1, P2, P3, or you can assume threads T1, T2, T3. In the perspective of deadlock, both can be same. Deadlock can happen to both process and threads. Now, for example, we have three processes or three threads. Assume that R1, R2, R3, R4 are resources. Okay. Now, the arrow mark towards the thread says that this resource is already assigned to thread 1. One instance of resource 2 is already assigned to T1. Now T1, in order to finish its execution, it is requesting another resource R1. Okay, so T1, one instance of R2 is already assigned to T1 and it is requesting one more instance from R1. Now R1 is already assigned to T2. Or R1 is already assigned to T2. Now T2 is requesting one more resource from R3. Also, one instance of R2 is also assigned to T2. Now R3 is requesting for T3. Okay, you see this, unless this T3 is finished, T3 is released, it completes its job, it cannot release this resource. Unless this resource is released, T2 will not finish its job. Unless T2 is finished, then only this resource will become free. Then only T1 will finish its job. So in order to finish T1, T1 needs R1, which was held by T2. So T1 is going in a deadlock state. Okay, T1 is already holding 1 and is requesting for R1, but R1 is already assigned to T2 and T2 is requesting for R3. So T1 cannot finish his job unless R1 is available. So T1 will go into a deadlock state. So that's what the example here is. A waiting thread can never again change state because the resources it has requested already are held by other waiting threads. Now here T2 is also waiting. T2 is also waiting because of resource R3, which was held by another thread T3. So T2 will not finish its job. Until it finishes its job, it will not release R1. T2 will not finish its job unless R3 it will be assigned to it. So T3 will also be in waiting. Unless T2 finish, T1 will also be in waiting. So T1 will go in deadlock state. So a deadlock is a situation in which every process in a set of processes, here we have three set of processes, T1, T2, T3. So deadlock is a situation in which every process in a set of processes is waiting for an event that can be caused only by another process in the set. Okay, in order to get the job done T1, T2 should release this resource. T2 will release only finishing his job. If R2 T2 has to finish, then R3 has to release. That will be released only when T3 finish job. Does this make sense? What is deadlock?
Yes, sir.
Anyone want me to repeat? Please try to understand. This is very important because if you don't understand this, nothing you will understand in the upcoming slides. So you can have multiple resources, and that is finite number of resources. We have only finite number of resources. The processes may keep coming. They are also finite, but compared to the resources, the process may be keep coming, but resources we have finite. That's what we started. In a multi-programming environment, several threads will compete for a finite number of resources. So a thread requests resource. If the resource is not available at the time, it enters into a waiting state. The waiting thread will never change its state because the resource it is requested will be held by another waiting threads. So this situation is called deadlock. Now, this will happen frequently in our operating system. Many applications can, some applications can identify programs that may have deadlock, but operating systems typically do not provide deadlock prevention facilities. Operating system, when we design, they don't provide these facilities. It remains in the responsibility of the programmers to ensure that design deadlock free programmers. As when you are designing a program, when we are writing an operating system, on when you are writing a program that is utilizing resources, your programmer responsibility is to design a deadlock free programs. Operating system will not prevent. Okay, but operating system in some applications can identify that programs may enter into deadlock situation, may identify, but it will not prevent. It is up to the programmer to ensure that the operating system will not go into a deadlock situation. So let us try to understand deadlock characterization. When at all the deadlock can happen. There are four conditions when where deadlock can happen. One is, the first necessary condition is mutual exclusion, which means at least one resource must be held in a non-shareable mode. That is, only one thread at a time can use a resource. If another thread requests that resource, the requesting thread must be delayed until the resource has been released. That's what the example we saw in the previous case, right? At least one resource must be held by in a non-shareable mode. So here R1 is not shareable because it is held by T2. R3 is not shareable because it is held by T3. So when such situation happens, then there is a possibility of deadlock. So at least one resource must be held in a non-shareable mode. That is, only one thread at a time can use a resource. If another thread requests that resource, requesting thread may be delayed until the resource has been delayed. This is one reason, necessary condition for deadlock. Hold and wait. A thread must be holding at least one resource and waiting to acquire additional resource that are currently being held by other threads. You are already holding one resource and you are requesting for other resource. So that is also another condition. This example can be understood by, for example, I will draw one even in a better way. Suppose, say that you have process P1, you have process P2, you have resource say R1, you have resource R2. Okay, now P1 is already is taking R2, it is requesting for R1. Now R1 is already assigned to P2 and P2 is requesting for R2. What is happening here? You see, P1, R2 is already assigned. In order to finish the process P1, it needs resource R1. Now R1 is already assigned by P2, assigned to P2. But P2, for it to complete, it needs resource R2. So P1 will wait for the availability of R1, which is held by P2. P2 will wait for the resource R2, which is held by P1. Both of them will keep waiting. This is called hold and wait. So a thread must be holding at least one resource, waiting for the acquire additional resource that are currently held by other threads. Is this clear? Hold and wait.
Yes, sir.
Okay, the third condition is no preemption. Resources cannot be preempted. That is, if a resources can be released only voluntarily by thread holding, after that thread has completed its task. So once the thread and resources is allotted, a process cannot leave in between. It has to finish its job. If it leaves, then deadlock may not happen. Suppose here P2 will leave the job, then R1 will be allotted to P1, P1 will finish the job. If P1 leaves, then R1 is allotted to P2, P2 will finish the job. So there is no problem of deadlock. But if the preemption is not happening, P1 is also not leaving, P2 is also leaving, then there is a problem of deadlock. No preemption is a necessary condition for deadlock. Okay, no preemption is a necessary condition for deadlock. Likewise, circular wait. This is also one example of a circular wait. So assume that you have n threads and a set of threads of waiting threads must be existing such that T0 is waiting for the resource held by T1, T1 is waiting for T2, and so on and so forth. Tn minus 1 is waiting for Tn, and Tn is waiting for T0. So there is a cycle, circular waiting. You understood that T1 is requesting, which is already hold a resources by T1. T1 is requesting another resource by T2, and so on and so forth. One after another it is depending. Tn minus 1 is requesting the Tn resource. Tn is requesting T0 resource. When this cycle happens, when there is a circular wait, then also there is a possibility it is also a necessary condition for deadlock. So deadlock characterization, if we are saying that a situation where a process or a thread, a system enters into a deadlock, these are the four important necessary conditions for a system to enter into a deadlock situation. One is mutual exclusion, and second is hold and wait, third is no preemption, and fourth is circular wait. If these four conditions are there, then a deadlock situation can arise in the system. Okay, so let us now try to understand the deadlock allocation graph in a more detailed way. So deadlock can be described more precisely in terms of a directed graph. It can be decided as a form of directed graph. We call that as a system resource allocation graph. So this graph consists of vertices and edges. As I showed in the previous example, this is a directed graph. There is a directions and you have vertices. Okay, you have vertices, you have directions. So what direction shows that as edges, process and resources shows that as a vertices. But these vertices are partitioned into two types. The set of vertices is partitioned into two types of nodes. One is threads consisting of all active threads in the system. Second one is resources containing all types of resources in the system. So if we assume that this is a resource allocation graph, so we will say that a directed edge from thread Ti to resource Rj will be indicated with Ti arrow Rj, signifies that Ti is requesting an instance of Rj and is currently waiting for that resource. Okay, the arrow mark towards from thread to resource says that Ti is requesting one resource instance from resource Rj. A directed graph edge resource from Rj to thread Ti. That is, you see this is a reverse direction. The arrow is pointing towards the thread. Okay. A resource type Rj to thread Ti. That is from Rj. This is reverse. If this is the case, then it signifies that that instance of the resource Rj is allocated to thread Ti. Rj is allocated to Ti. So directed edge Ti to Rj is a request edge. Directed edge Rj to Ti is an assignment edge. There is a difference. Is this clear? So like this, when I say that it is Rj, Ri to Ti, so when the arrow is pointing from resource to Ti, it is saying that it is assigned. When an arrow is pointing from thread to resource, it is requesting. Okay, requesting, that is request edge, assignment edge. They both are different. So here resource instances are R1 is one type of resource instance, R2 you have two resource instances, and one type of R3 resource type of R3, and three instances of R4. What are the thread states? Thread 1 is holding an instance of R2 waiting for an instance of resource type R1. What is the status of thread 2? Thread 2 is holding a resource instance of R1 because the arrow is pointing towards resource to Ti, Rj to Ti, that is thread T2 is holding an instance of R1 and an instance of R2 and is requesting R3. Thread T3 is holding an instance of R3. So you can write like this. Edges can be written as T1 to R1, that is T1 to R1, T2 to R3, T2 to R3, and R1 to T2, R1 to T2, R2 to T2, R2 to T2, then R2 to T1, R2 to T1, then R3 to T3. So the edges will represent this situation, thread states and the resource instance. This we call that as a resource allocation graph. Is this clear?
Yes, sir.
Okay. Now, given the definition of resource allocation graph, it can be shown that if the graph contains no cycles, then no thread in the system is deadlocked. If the graph does contain cycle, then there may be a deadlock exists. Okay. If there is a cycle, is there a cycle here? Yes, there is a cycle. So this T1 will go into deadlock state. You see this? There is a cycle here. Okay. So if there is a cycle in the graph, if the graph does contain a cycle, then deadlock may exist. You say this is a may. Why may? Because if each resource is having only one instance, and if you are having a cycle, then surely there will be a deadlock. If a resource will have multiple instances, for example, let us assume that there is one more instance of R1. There is one more instance of R1. Then if T1 is requesting R1, R1 can be allotted. This is free. It can be allotted. Then there is no deadlock. But still there is a slight cycle. But there is no deadlock. When there will be no deadlock, when the resources instances are more than one. If resource instances are more than one, then even though the cycle exists, deadlock may not happen. But if you have only, like I showed in this example, you have only one resource, you have only one resource instance. If there is only one resource instance, then if the cycle forms, there is a cycle, then deadlock will surely happen. Deadlock will surely happen. Okay. So if the graph does contain, then deadlock may happen, because if the resources are only one, then it will surely happen. If the resources are multiple, even though cycle exists, it may not happen. So for example, in this case, tell me the deadlock is there, right? Can you tell me there is a deadlock? So T1 is holding R2 and is requesting for R1. T2 is holding R1 and R2 is requesting for R3. T3 is holding R3, then is requesting for R2. So you see this, there is a cycle here also, and there is a cycle here also, and there is a big cycle here. So T1 to R1, R1 to T2, T2 to R3, R3 to T3, T3 to R2, then again R2 to T1. So this is a big cycle. Yes, there is a deadlock. Likewise, T2 to R3, R3 to T3, T3 to R2, again R2 to T2. So again there is a cycle here. Again there is a cycle here. So this is also deadlock. So when there is a cycle, there is a good chances of deadlock will happen. So if each resource type has exactly one instance, then cycle implies the deadlock has occurred. If the cycle involves only the set of resource types, each one of only having only single instance, then deadlock occurred. If a thread involved in the cycle, then it is deadlocked. In case the cycle in the graph is a both necessary and sufficient condition for in this case, when the single instance is there, cycle in the graph is a necessary and sufficient condition for the existence of deadlock. There might be some examples where you can see that deadlock is not will happen. So if the resource has several instances, then cycle does not necessarily imply that a deadlock occurred. For example, in this case, T1 to R1, R1 to T3, T3 to R2, R2 to T1, but there is no deadlock because uh, T1 is holding one resources of R2, but T4, if it is finished, then this resource will be allotted to T3. After that, T3 will be relieved. T3 relieved, then this resource can be relieved. Or else, if T2 finish his job, then R1 will be released. This instance can be given to T1. T1 will finish his job. After T1 is finishing, R2 will also be free, can be allotted to T3. So although there is a cycle, there is no deadlock here. Okay, but in this case there is a deadlock. Okay, there are no more instances that can be relieved. So you have to be very clear when the system will go into deadlock or not. Cycle may lead a system into a deadlock if it has only single instance. If the resources is having multiple instances, then deadlock is not happens. It's not the sufficient condition to happen for the deadlock. Okay, is this clear? You want me to repeat this, guys?
Yes, sir.
Listen, here is the deadlock when T1 will finish his job. T1 is already having resource R2. It is requesting for R1. T1 will be not able to finish his job until T1 gets R1. Correct? Is this clear?
Yes, sir.
Now when R1 is free, No, R1 is not free, right? R1 is assigned to T2 because the arrow is showing towards thread. So R1 is already allocated to T2. Also, R2 is also allocated to T2. Now, when T2 will finish his job, in order to finish T2, it needs resource R3. Now, R3 is free? No, R3 is not free because R3 is allocated to assigned to T3. Now, when T3 will finish his job, in order to T3 finish it, it is requesting another resource from R2. So from R2, one resource is allocated to T1, one resource is allocated to T2. There are no more resources available in R2, but T3 is requesting R2 to finish, but there are no resources available. So T3 will keep in waiting state. This will be allocated, no preemption. So unless T3 finish, this resource cannot be free. So T2 will go in waiting for R3. T2 will not finish because T3 will not finish because there are no resources available in R2, extra resources. Now T1 will also keep in waiting because it is requesting for R1 and R1 is sold by T2, right? So clearly there is a deadlock is happening here. Now one way to identify deadlock is you have to see that the cycle is there or not. The cycle, see here, T1 to R1, R1 to T2, T2 to R3, R3 to T3, T3 to R2, R2 to T1. Is there a cycle here? T1 to R1, R1 to T2. This is cycle, right? Cycle means what? Where you started, you will end up at the same position. You started with T1, you went, traversed all the vertices and came back to T1 only. You start with T2, T2, R3, T3, R2, again T2. This is also a cycle. When there is a cycle, then there may be a formation of deadlock. In this example, deadlock is there. In this example that we are discussing, there is a deadlock. Okay, resource allocation graph with deadlock. There is a deadlock. Is this clear?
Yes, sir.
Now let us see this example. This example, T1 is R2 is allocated to T1, is requesting for R1. R1 has two resources. One is allocated to T2, one is allocated to T3. And T3 is requesting for R2, but R2, one is allocated to T1, one is allocated to T4. Now tell me, is there a cycle here? Yes. T1 to R1, R1 to T3, T3 to R2, R2 to T1. Is there a cycle? Yes, but this cycle is not sufficient for deadlock because R1 is having multiple instances. Multiple instances means R1 has two resources. One resource is sold by T3, which is requesting R2, which is sold by T1. But after some time, T2 will finish his job. If T2 finish this job, this node will go away. Now, this resource will become free. If this will become free, this can be allocated to T1. After allocating to T1, T1 will finish his job. This will also be free. After finishing, so T1, this resource will be free. This resource will be free. Now T3 can use this resource. Is this clear?
Yes, sir.
Or else the other way is, the other possibility is, you see this other possibility is, now after some time T4 will finish his job. this resource will become free. If this resource will become free, what will happen? This resource is allocated to T3. If this resource is allocated to T3, T3 will finish his job. So this will be no longer after some time. T2 will finish his job, the resources will be available, and T1 will get the job done and it will also finish. So there is no deadlock. But there is a cycle, T1 to T3, T3 to R2, sorry, T1 to R1, R1 to T3, T3 to R2, R2 to T1. There is a cycle. Why? Even though there is a cycle, there is no deadlock because we have several instances. The resource type, you have several instances. If several instances are there, cycle does not imply the deadlock. It's not a necessary, but it's not a sufficient condition for the existence of deadlock. May be there or may not be there because of multiple instances. Now, for example, this same example, I will redraw this. T1, you have R1, you have T3, you have R2. So imagine you have only one instance, only one value of R2, only one value of R1. Now T1 is requesting R1, but R2 is allocated to T1. R1 is allocated to T3, and T3 is requesting for R2. Is there a cycle now? Is there a cycle?
Yes, sir.
Yes, there is a cycle because T1 you are getting matched back to T1 only. Now, is there a deadlock?
Yes, sir.
Yes, because we have only one instance. R1, R2 is having only one instance, and each instance is allocated to each process. So that's what I'm saying. So if each resource has exactly one instance, then cycle implies that deadlock has occurred. If cycle involves only a set of resource types, then single instance deadlock has occurred. Each thread involved in the cycle is deadlocked. Okay, each thread T1, T3 both are deadlocked. In this case, cycle in the graph is both necessary and sufficient condition for the existence of deadlock. So cycle in single instance is there, single instance of R1, R2, single instance of resources. If it is there, then existence of cycle will lead to deadlock. Here we have two resources, R1, R2. Here also R2 has two resources. Because of two instances, cycle will not lead you to deadlock. So in this case, cycle is a necessary but not sufficient condition. In this case, a cycle in the graph is a necessary but not a sufficient condition for the existence of deadlock. Is this clear? What is your doubt? Why you are not able to understand this? What is your question? If you are not able to understand this, ask any question. Otherwise, you will go ahead.
रिसोर्स एलोकेशन कैसे हो रहा है सर, एक बार रिपीट कर दीजिए.
Resource allocation. Resource, see the arrow, if it is pointing, R2 is pointing to T1, means R2 is allocated to T1. If there is an arrow from resource to thread, which means resources is allocated. If there is an arrow between thread to resource, then it is requesting. This is request. This is request. This is allocated. Where the arrow is pointing? From where to where the arrow is coming?
T2R.
R2 to T1. So R2 is assigned to T1. Now T1 is requesting R1. because the arrow is pointing from T to R. T to R is requesting. If this requesting is assigned, then if resource R1 is allotted to T1, then the arrow will be in the reverse direction. Resource to T. If resource to T is the arrow, then it is allocated.
Yes, sir.
Is there any other doubts? Okay. So let us now try to understand how we can handle the deadlocks. Generally speaking, we can deal the deadlock problem three ways. One is ignore the problem altogether, pretend deadlock never occur in the system. Because it happens, deadlock happens, and what happens when the deadlock happens, the process will go and keep on waiting stage, and it will never finish. It will deteriorate the performance of the system. You can ignore altogether the deadlock is not happened occur in the system, or we can use a protocol to prevent or avoid the deadlocks, ensuring that system will never enter into a deadlock state. So before going into deadlock state, we have to prevent or avoid the deadlocks. Then the third is, if the system enter into the deadlock state, we have to detect it and recover it. So there are three steps. Ignore the deadlock happened, do whatever it like. Second is prevent or avoid the deadlocks before entering into the deadlock state. Third is once the system is entered into the deadlock state, we have to detect some deadlock happen and we have to recover back to the original state. So these are the three possible ways. Now ignoring is not a problem, you ignore it. Some operating systems, they ignore. The performance of the operating system will be very bad if they ignore the deadlocks, because each process will keep on waiting and making other process waiting, so it will become too slow. Your system will become too slow because of deadlocks if you ignore it. Okay, if you can able to prevent and avoid, or if you can able to detect and recover, then your performance of the system will be increased. So to ensure deadlocks never occur, the system can use deadlock prevention or deadlock avoidance scheme. This is second stage, second step. We can prevent or avoid the deadlocks. Before deadlock happens, to ensure deadlock never occur, the system uses deadlock prevention or deadlock avoidance scheme. What is deadlock prevention? Deadlock prevention provides a set of methods to ensure that at least one of the necessary conditions cannot hold. One of the necessary conditions is either this four conditions: mutual exclusion, hold and wait, no preemption, circular wait. These are the four conditions. If these four conditions, at least one of them cannot hold, then you can prevent the deadlock. This method prevents the deadlock by constructing, however, request for the resources can be made. The second is deadlock avoidance. How you can avoid the deadlock? Requires an operating system need to have some additional information in advance which resource a thread will request during its lifetime. But with this additional knowledge, operating system can decide for which request whether or not thread should wait. So we need some advanced knowledge of the resources for a particular thread request and their lifetime. If you know that, then we can allocate the resources to particular threads by making sure that the system will not go into the deadlock state. So to decide whether the current request can be satisfied must be delayed, the system will consider the resources currently available, the resources currently allocated to each thread, and the future requested and releases of each thread. We will discuss this in detail algorithm. Okay. So in this case, undetected deadlock will cause system performance to deteriorate. Resources are being held by threads cannot run because more and more threads, and to make more requests, the system will enter into a deadlock state. Eventually, the system will stop functioning and it needs to be restarted manually. Okay, so this is the main problem of deadlocks. So let us now discuss deadlock prevention. In 6 and 11 slides, we discussed that there are necessary conditions are mutual exclusion, hold and wait, no preemption, circular wait. These 4 conditions must hold. So by ensuring at least one of these conditions cannot hold, we can prevent the occurrence of the deadlock. So if there is a mutual exclusion must hold, that is at least one resource must be non-shareable. So shareable resources do not require mutual exclusive access and cannot be involved in a deadlock. For example, there are read-only files. Read-only files are good examples of a shareable resources. Several thread attempts can open a read-only file at the same time. They can be granted simultaneous access to the file. A thread can never needs to wait for a shareable resources. So if the file is only read, then multiple threads can come and read because there will be no change because there is no writing. If the file is read only and it is shareable resources, multiple process can come and execute. Okay, that's not a problem. Shareable resources in a thread never needs to wait for a shareable resources. However, we cannot prevent deadlocks by denying the mutual exclusive condition because some resources intrinsically are not shareable. Some resources, all resources are not shareable. For example, mutex lock. Last time we discussed, mutex lock cannot be simultaneously shared by several threads. Mutex lock is only one lock, it will enter into critical section. Because only one lock will enter in the critical section, it will come in a non-shareable basis. Whenever there is a non-shareable basis, there is a mutual exclusion. We cannot provide mutual exclusion. So because of this reason, we cannot prevent the deadlocks by denying mutual exclusion condition. So this is not practical. Okay, mutual exclusion is not practical because all the resources are not shareable. Some resources are shareable, some resources are not shareable. If the resources are not shareable, we cannot ask to execute multiple files. We cannot hold the mutual exclusion. Okay. What about hold and wait? To ensure hold and wait condition, it will also never occurs in the system. We must guarantee that if it is whenever the thread requests a resources, it does not hold to any other resources. Okay, hold and wait means it is holding one resource, asking for another resource, waiting for another resource. If we can avoid this situation, then we can prevent the deadlock. One protocol we can request for such thread to request allocated its resources before its execution. Okay, one protocol that we can use requires each thread to request and be allocated its resource before its execution. But this is impractical because most applications are dynamic programming, dynamic nature of requesting resources. Because of dynamic nature, we don't know when requests will be requested. An alternative protocol is a thread to request resources only when it has none. Thread may request some resources and use them. Before it can request any additional resources, it must release all the resources that is currently allocated. So these both conditions, hold and wait, one way is to make sure that before starting itself, we will not allocate. We will not make one resource. For example, you have P1, R1, P2, R2. If we know that P1 is taking R2 and is going to request R1, then don't allot P2 to R2. Don't allot this resource to P2. If you have the knowledge, then P1 will allocate it to R1 will allocate it to P1 only. This job will finish. Then both resources will be free. P2 can also finish. If we have the knowledge that P2 needs R2 and it is going to request R1, it is already hold R1, it is going to request R2. If the knowledge we have, then hold and wait we can avoid. For that we need to have this is impractical because we need, most applications are dynamic. We don't know which process will request which resource. We don't know. So this is impractical. Alternative protocol is that thread to request resources only when it has none. So P1 will request only when, if P1 is not having resources R2, not R1. If P1 is not holding any resources, then if it is requesting, then also it will not enter into deadlock, because if R1 R2 is not held by P1, P2 will take all the resources, it will finish job. Now P2 will also not hold any resource, R1 R2 will be free, it will allocate to P1. So an alternative approach is allow the thread to request resources only if it has none. But a thread may request some resources and use them. So before it can request additional resources, it must release all the resources which is currently allocated. That also not possible, because this both has disadvantage. First, the resource utilization may be low in this first case, because resources may be allocated and unused for a long period. For example, a thread may be allocated to a mutex block for its entire execution, yet only require for a short duration. Second, starvation is possible. Whenever a thread needs a popular resources may have to wait indefinitely, because at least one of the resources that it needs always allocated to some other thread. Now suppose in this case P1 is not holding any resource, P2 is there, P2 is using R1 and R2, and P3 is coming. P3 is coming and it is taking R1 and R2. P4 is coming. P4 is also coming on R1 and R2. So P1 is keep on waiting. P1 is keep on waiting to get R1 and R2. So that is called starvation. When when a thread requests, when a thread releases all the resources which is currently allocated, there is a good chance that it will go into a starvation, because other processes which are coming may take hold of these resources till the system may enter into deadlock situation. So hold and wait also having some disadvantages. Now third is no preemption. If the thread is holding some resource and requests another resources that it cannot immediately allocated to it, then all the resources in the thread currently holding are preempted. Means it will leave in between, it will go and wait for some time, it will be reallocated. So the resources are implicitly released. Forcefully, the resources are released. The preempted resources are added to the list of resources for which the thread is waiting. The thread will be restarted only when it can regain all old resources as well as new ones that is requesting. So this is one possible. Alternatively, if a thread requests some resources, we first check whether they are available. If they are available, we allocate them. If they are not, we check whether the allocated of some of the thread that is waiting for additional resources. If so, we preempt the desired resources from the waiting thread, allocate them to the requesting thread. If the resources are neither available nor held by the waiting thread, the requesting thread must wait. While it is waiting, some of the resources may be preempted, but only if another thread requests them. So what happens here is, let me show this example. Suppose in this example, preemption means now T1 will leave the job. If T1 leaves, R2, R1 will be, R2 will be available. If this job is not there, this T1 leaves the job, it's preempted. What happens if it is preempted? R2 will become available, right? This resources which is held by T1, R2 will become available. R2 will be allotted to T3. T3 will finish his job. Now T3 finish job, this resource will be available. This is also available, then T2 will finish his job. For this, one process T1 should leave it, or any other process should leave it, preempt it. If that is the case, then we can avoid the deadlock. We can prevent the deadlock. Okay, that's what we are discussing. So implicitly released, forcefully released. Now what happens if a thread requests some resources? We first check whether they are available. If they are available, we allocate them. If they are not, then the system may enter into deadlock. So we will check whether the allocated to some of the other threads that is waiting for additional resources before requesting. So in this case, before, let us assume that before T3 request happens, R3 will be not allotted to T3. In this example, we will check that T3 is going to request R2, which is holding R3. So we will not allot R3. If it is going to happen in a deadlock state, we will not allocate in R3. That was this sentence means. If they are not available, we check whether they are allocated to some other thread that is waiting for additional resource. If so, we preempt the desired resource from the waiting thread and allocate them to the requesting thread. So we will preempt, in this case, we'll preempt T3. We will allocate this resource to R3. Now T2 will finish his job. After T2 finished, R1 will be given to T1. T1 will finish his job. Okay. So here T3 can be removed. Okay, so in this case, the preemption, by forcefully uh, making that one process to leave, one thread to leave, then we will prevent the deadlock. If the resources are neither available nor held by any waiting thread, then the requested must wait. If the resources is not available, then thread has to wait. While it is waiting, some of the resources may be preempted, but only if the another thread requests them. If thread can be restarted only if the allocated new resource is requesting and recovers any resource when preempted while it is waiting. So this is the third condition. This protocol is often applied to resources whose state can be easily saved and restored later, such as CPU registers, database transactions, where it is possible. But it cannot generally applicable to resources on mutex locks, semaphores, precisely where the resource deadlock occurs most commonly. You cannot preempt a process in mutex. You cannot preempt a process in semaphore because of critical sections. In such sections, only deadlock occurs more commonly. Then this preemption cannot be applicable at such places. Okay. Then the fourth condition is circular wait. After this, we will take a break. I will give some time to discuss. So the three options for the deadlock which we discussed are impractical: mutual exclusion, hold and wait, preemption. Both of them are impractical in most situations. However, the circular wait can give some benefit to prevent the deadlock. The fourth and final condition for the deadlock, circular wait condition, presents an opportunity for practical solution by invalidating one of the necessary conditions. One way to ensure that this condition never holds is to impose a total ordering of all the resource types to acquire that each thread requests resources in an increasing order of enumeration. So increasing order of enumeration, if you do, then what will happen is we will give some ranking. In each rank, or we will sort them as per the uh, order. We will keep them in one order. Okay. So each process will request the resource in an increasing order, of the enumeration. Now we say, suppose let us say that a thread can initially instance of resource Ri, then after the thread can request an instance of Rj if and only if the order of f of Rj is greater than f of Ri. If this order is maintained, then whichever order is higher, then we can allocate the resources first to that, then making the other resources to wait for some more time, then you can prevent the deadlock. So we have to keep in mind that when we are developing an ordering or a hierarchy, which does not prevent the deadlock, because developing such order or a hierarchy will not itself prevent. Okay, but it may help us to decide to avoid to some extent. After deciding the rank also, there will be some cases it may enter into deadlock. Okay, so this is the last circular wait. Before entering into deadlock avoidance, I will give some time. Let us take a break. We will get back to this again. Before discussing deadlock avoidance, we will take 5-10 minutes break. Okay, shall we get back? We'll finish soon. We'll try to finish soon, and we will leave. Okay. So let us now try to discuss the deadlock avoidance. How we can avoid it. Okay. So the deadlock avoidance algorithm dynamically examines the resource allocation to ensure that circular wait condition can never happen. Which means the deadlock avoidance to prevent the deadlock preventing algorithms can prevent the deadlock by limiting how many requests can be made. The limits ensure at least one of the necessary conditions for the deadlock cannot occur. But if you do that, there will be some side effects like low device utilization, reduced system throughput. The best other method is to go for deadlock avoidance, which will require some additional information how resources are requested. Okay, how resources are requested. For example, we will discuss some example. The resource allocation state is defined the number of available allocated resources and the maximum demands of the threads. So before defining deadlock avoidance, let us understand what is a safe state. A state of safe. This is a safe state we will define. Based on the safe state, we will check before allocating some resources, the system will go into safe state or not. If it is in safe state, then we will see that how we can carry out. If it is not in unsafe state, then surely the deadlock will happen. So a safe state is if the system can allocate resources to each thread in some order and still avoid a deadlock. So we have to allocate resources in particular order only to avoid deadlock. More formally, a system is in safe state only if there exists a safe sequence. A sequence of threads T1, T2 and so on Tn is a safe sequence for the current allocation state if the resources request by Ti can still make a satisfied with the current available resources plus resources held. If this condition satisfies, then we can say that it's a safe sequence. So this is a deadlock avoidance diagram. You say that this blue color is unsafe. If it is in unsafe, deadlock will surely happen. If it is in safe, deadlock may happen, may not happen. Is this clear? If it is unsafe state, deadlock will surely happen. If it is safe state, deadlock may happen or may not happen. Because for this time T0, the system may be in safe. At time T1, when some other process is requesting some other resources, when you are allocating them, again you have to check that whether it is a safe or unsafe. If you do something wrong allocation, if the system will go to unsafe, then again it will come into deadlock. Okay. So when we can say safe, I will tell you by one example. Suppose, let us see that one example, then this will make more sense. So let us say that we have 12 resources, 3 threads. We have total 12 resources. We have 3 threads. Maximum need for each thread is T0 10, T1 4, T2 9. Current need, which is currently need is based on how many resources it is holding. So T0 is holding 5 resources. So T0 is holding 5 resources, maximum is 5. So current need is 5. 10 minus 5 will be 5. T1 is holding 2 resources. So 4 minus 2, The current need is, it needs 2 more resources to finish. T2 is holding 2 resource, okay, and it needs another 2 more resources. Okay, now we have only assume that now how many resources are there? 5, 2 and 2. If there are 2 resources here we are keeping, then here this should be, current need should be 7. This is a mistake. The current need should be 7. Okay, now 5 plus 2 plus 2 is 9. 12 minus 9, we have 3. So available resources are, free resources are 3 resources. Now we have to allocate in some way the deadlock we can avoid. Which thread we will allocate first? T1 need only 2 resources. If 2 resources we give to T1, T1 will finish and it will free 4 resources. Then available resources will become total 5, correct?
ఈ పిల్లలు అయిపోయినట్టుంది సామి.
ఎలా వచ్చినాయి కొడుకు
Okay, somebody mic is mute, not mute. Please pay attention here, guys. Assume that we have 3 resources. T0 is holding 5 resource, T1 is holding 2 resource, T2 is holding 2 resource. This is the maximum need. Now current need is holding minus maximum is the current need. Okay, this you will get. Now we have 3 resources. If you allocate these 3 resources to T0, this system will go in unsafe state, because in order to finish T0 it needs 2 more resources. Where we will go for where we will go for 2 resources? There is no possibility. If we allocate T1 first, if we allocate T1, this 2 out of 3, these 2 resources you can allocate, then T1 will finish its job. So we have 1 resources here, 2 resources we gave, so total 4. So 4 plus 1, you will get 5 resource. This 5 resource you can allocate to T0, because T0 is having need of 5. This 5 resources we allocate to T0, then T0 will finish his job. Then we will get, after finishing his job, we will get 10 resources in our hand. After getting 10, we can allocate 7 resources to T2. Then every job we will execute without entering into deadlock. So the sequence T1, T0, T2 satisfies the safety condition. Okay, the order in which we are allocating the resources makes whether the system is in safe or not. If we allocate in this order, the system will enter into safe condition. If you allocate T0 or T2 first in any other order, it will not be enter into, a system can go from safe state to unsafe state. Suppose at time T1, T2 requested this resource. So okay, so now you allocated first out of 3 to this guy. After some time, if you allocate T1 to T2, then you cannot allocate to T0. Then again system will go into unsafe state. Okay, so that's what at time T1, T2 is requesting 1 resource, then system is no longer in safe, because at this point only T1 can able to allocate the resource. It will return them only with 4 available resource. T0 is allocated 5 resources, which has maximum of 10. It has maximum of 10. Now this will become need of 6, but you need 5 here. Available are only 4, because out of this will be the 1. Okay, let me rewrite again. You understood how this went into safe state? By allocating T1, T0, T2, we will make into safe state. Now let us assume that it will go to unsafe state. Now what will happen? Now suppose T1 out of 3, T1 needs 2, so these 2 resources is allocated. This 2 resources is allocated. T1 is finishing his job. So free resources available is 3 minus 2, 1 resource. If we allocate this 1 resource to T2, this should be 7. Okay, this should be 7. If we allocate this 1 resource to T2, what will happen? This will become 0. This will become 6. But after that, T1 will finish. T1 will give 4 jobs back. Now from 6 you can if you allocate 4, still it will be in waiting state. Out of 5, if you allocate 4, still that will be also in waiting state. This will go into unsafe place. So that's what we are explaining here. A safe state, a sequence of threads is a safe sequence with the current allocation state if for each Ti, the resource request Ti can make based on the current available resources plus resources held. Okay, if we have to put in a proper order, then only we can say that is a safe. From safe state, again, a system can go to unsafe state. Okay, that's what we explain here. So in this situation, if resource Ti needs not immediately available, then Ti can wait until all the rest of Tj have finished. When they have finished, Ti can obtain all the needed resources completely to its designated task, return all the allocated resources and terminate. Ti terminates, Ti plus 1 can obtain all the needed resources and so on. If no such sequence exists, then system will be set into unsafe state. If there is no such sequence, here, then the system is in unsafe state. If system is going to unsafe state, it will happen, deadlock will happen. So a safe state is not a deadlocked state. Conversely, a deadlocked state is an unsafe state. Deadlock state is an unsafe state. Not all unsafe states are deadlocks. However, unsafe state may lead to deadlock. As long as the state is safe, operating system can avoid unsafe states and avoid deadlock. In an unsafe state, operating system can prevent threads from requesting resources in such a way that deadlock occurs. The behavior of the threads controls unsafe states like this. Okay, so this, if you do allocate T1, then system may enter into unsafe state. Okay, so the mistake is you should not grant this 1 resources available to T2. If you allocate, then it will go to unsafe state. So we have to be careful. So this is one way we have to remember what is the safe state. Okay, having understood the safe state, now let us explain 2 algorithms how we can avoid the deadlock. One is simple resource allocation graph algorithm. In this algorithm, if there is a cycle, the requested resources are put are you can see here, are kept or put in dotted line. So we have resource allocation system with 1 resource instance of each resource type, and we say that if there is a cycle exists, then there will be a deadlock that we define. In addition to that, we will define one more parameter here. If there is a request and assignment edges already described, now we will introduce a type of edge called claim edge. This claim edge is determined in dotted arrows. Now suppose a thread Ti request and request Rj. If this dotted line is making a cycle, if after dotted line before allocating, we did not allocate it, we are just verifying the claim. By claiming, by dotted line before allocating, if there is a cycle, then we will not allocate. We will check for other ways. After claiming edge, we will check for the safety by cycle detection algorithm. If there exists a cycle, then we will not allocate it. It will not be safe. We will go back to the previous state. If no cycle exists, then the allocation of the resources will leave the system in a safe state. If the cycle is found, then the allocation will put the system in unsafe state. In that case, that particular order of allocation has to wait for that request. So the algorithm detecting the cycle in this graph can take n square operations, where n is the number of threads in the system. Okay, so simple resource allocation graph algorithm. There is another algorithm called Banker's algorithm. This Banker's algorithm we will discuss. Then we will come to an end of deadlocks. So resource allocation graph algorithm is not applicable if resource allocation with multiple instances, that we already discussed. If resource has multiple instances, then this algorithm will not work. This will work only with each resource having one instance. If there are multiple instances, then we can go for Banker's algorithm. The name why the Banker's algorithm is chosen because banking systems will ensure the bank never allocate its available cash in a such a way that it will be no longer satisfies the needs of all the customers. The bank will ensure such algorithm, they will allocate the cash to the available resources to the ATMs in a such a way that the bank will no longer end up in cashless. Okay, that should not happen. That's why this algorithm is usually applicable for banking system. The same algorithm we will applicable in deadlock situations. Several data structures we need to encode for the state of resource allocation system. We need to understand the following data structures, where n is when n is the number of threads and m is the number of resource types. So let us say that available, we need to check the available. Available vector indicates the number of available resources of each type. If available j equals to k, then k instances of resources are available. Maximum. Maximum is an n cross m matrix, defines maximum demand of each thread. If maximum of ij is equal to k, then thread ti may request k instances of resources rj. Likewise allocation, likewise need. Need you will get by subtracting maximum from allocation. Okay, let us see this example. Suppose this is the allocation already allocated. We have 5 threads, T0, T1, T2, T3, T4. We have 5 threads. These are the allocated. We have three resources, instances you can say. A, B, C are the 3 resources which are available. This is the vector. Available is a vector. So it tells that how many resources are available. Allocated, this is a matrix, n cross m matrix. So resources of A type allocated 0 to A. I mean for T0, A type of resources allocated are 0, B type of resources allocated are 1, C type is 0. For T1, A type allocated 2, B type 0, C type 0, and so on and so forth. The maximum demand is A. For T0, A needs 7, B needs 5, C needs 3. Okay, so this is the maximum need, maximum required. The need we will allocate simply max minus allocation will be the need matrix. Max minus allocation is the need. Now this is what we defined here. So the available is a vector which indicates the available resources, that is this one available. The allocation maximum n cross m matrix, the maximum demand of each thread. This is the maximum demand of each thread. Allocated, the number of resources which are currently allocated, that is allocated matrix. Then fourth is need matrix. How much is the need? That will be maximum minus allocation will get the need. Now we have this many resources available. This is a need. If you can't allocate to T0, because if you allocate to T0, then this will be no longer safe. Can you allocate to T1? Yes, you can allocate because available 332. This is satisfying. You can allocate to T1 also. You can allocate to T3 also. Okay, after T1 allocation, then how many resources will get free? If 3 resources, the need is 1. So this will become, you allocate to T1. T1 is considered first. because the need what is there based on availability, it is meeting. We can allocate safely, no issues. So one resource of A you can allocate to T1. Need is 2, so here 1. Again C needs 2, so 0. So T1 will finish his job. Can you allocate any other resource? 210. Is there anyone satisfying? No. Then other process will keep waiting. After T1 finished, then now availability will be 3 resources of A we will get, right? We'll get back of 3 resource. So this will become, after T1, this will become 3 plus 2, this will become 5, because 3 resources released from T1, 2 already we have. 3 plus 2 will get 5. Maximum 2 will also be free. So 2 plus 1, 3. Then again 2 resources we will get. This is available. Next save sequence, can you allocate T2? No, because A resource is having 5. This is having 6. We cannot allocate T2. Can allocate T3? Yes, we can allocate T3. If we can go for T3, then this will become 5, 2, 1. So this T3 will be doing his job. After doing, can you allocate to T4? No, you cannot allocate because B needs 3, but we are having only 2. So T4 will wait until T3 finished. After T3 finished, so this will be added here. After T3 finished, the available resources are 7, 4, 3. Now can you allocate T4? Yes, you can allocate to T4. Can you allocate after that to T2 and T0? Yes. Now the system will go in safe without any problem. So first we have to check the safety algorithm. The safety algorithm is the work unfinished by vectors. We can allocate work is equal to available, finish is equal to false. For each index, we keep work is equal to false, need less than or equal to work. If the work plus allocation is equal to work, then make that as a true. Otherwise, go to step 2. Keep doing this. Whichever is true, then allocate the system in a safe state. This algorithm will require m(n) square operations to determine the system is safe. If the safe is system, then requested if it is less than or equal to need, then if requested is less than or equal to available, then available will become available minus request, allocation will become allocation plus request, need will become need minus request. We can carry out the sequence. So T1, T3, T4, T0, T2, T0 satisfies the safe sequence without entering the system into deadlock. We can avoid the deadlock using Banker's algorithm. Okay. So T1, after requesting one additional instance of resources A type, 2 instance of resource T type will be given 102 to decide whether you can keep checking that we discussed already. So we will arrive the new state. So this is the case 230. Suppose let us determine, we can able to determine whether this is in a new system is in safe or not. Now we can allocate 230. This is the need. We can allocate first T1 because this is meeting the need. You can allocate T1. You can allocate T3 after that, because after that you will get the resources free. Because 2 will be released, 1 you can allocate here. Then again you can allocate T4, T0 satisfies the safety requirement. But after this state, when you allocate the system, after 330, T4 cannot be granted because resources are not available. You can keep checking the Banker's algorithm how we discussed. That will be helpful. Okay. So let us see for this example. How much? What is the time now? 4:34. Okay. So this is a need. This is available. So which resource is meeting? 230. So T1 will allocate. So this T1 will be done its job. If you allocate this resource, what will happen? What will be available? 2, 3 minus 2, 1. This will be 0. After T1 finished, this we will get 3 we already allocated. This will be free. So this will become 5. So 2 allocated now. 2 that will become free. This will become 3. 2 already here. This will become free. So 5, 3, 2 will be free. Now can you allocate T3? Yes, T3 can be allocated. If you allocate T3, this will become 5, 2 and 1. After finishing its job, now 2 resources will come here. So this will give you 7. 2 plus 1 plus 1. This will become 4. 1 plus 1 plus 1. This will become 3. So after 3, 3, can you allocate T4? 4, 3, 1. Yes, you can allocate. This will become, after allocating T4, this will become, resources available will become 3, 1, 2. Okay, after this, can you allocate T0? No, we need these resources back. So after T4, this 4 will be added. Again, this will become 7. This will become 3, 4. Then 2 plus 1, 3 plus 2, 5. We'll get this state 3, 7, 4, 5. Can you allocate T0? 7, 4. Yes, you can allocate. T0 can be allocated. So this will become 0, 0, 2. Can you allocate to T2? No, it will wait. So after finishing this stage will become 7, 4 plus 1, 5, 3 plus 2, 5. Can you allocate now to T2? Yes, T2 can be allocated. So if you allocate T2, then this will become 6. You will allocate. So this will become 1. 7 minus 6, 1. This will be 5 and 5. After finishing its job, so 6 plus 3, 9 plus 1. This will become 10. So this will become 5. This will become 7. So these are the available resources. So without any problem, we should be able to see that the system went into the safe state. So this is how the Banker's algorithm works with multiple instances, multiple need and multiple availability. Based on the availability, we will check the need. If the request is less than or equal to need, go to step 2. Otherwise, raise an error condition. If the request is less than available, then go to step 3. Otherwise, T1 will wait in that state only. If the system requested available and the need is there, then you can allocate the resources. After that, it will become free. Then you can keep doing that. So that's how we will carry out the Banker's algorithm. Now, we discussed there are 3 steps: deadlock prevention, deadlock avoidance. After the system enter into deadlock, how we can recover. So this we will discuss and we will stop. One way to recover from the deadlock state is terminate. Process and thread termination. We can abort all the process, all the deadlocked process, start from fresh, or abort one process at a time until the deadlock cycle is eliminated. One question will rise is which process will be eliminated when you are choosing from one at a time? Which process should be aborted? We should abort the process whose termination will incur the minimum cost. Minimum cost means, in the term of minimum cost, they include many factors. Which process should be chosen? Maybe what is the priority of the process, how long the process has computed, how long the process will compute before it's completing its designated task, how many and what types of resources process has used, how more resources and process need to order into complete, how many process will need to terminate it. Based on this all factors, we will choose a process with minimum cost. We will terminate the process. Make sure that the deadlock is free. If the deadlock is not free, then you go for another process. You can go for another process. You can choose that process, kill that process, abort the process. Okay. Otherwise, resource preemption is another possible. Choose a process to terminate, which should be determined in the order of preemption in the cost of minimum cost. Abort or preemption is more or less same. It is leave the execution, it will go back and waiting state, start from restart. So this is also same as abort only, but here also we have to choose the factors based on number of resources deadlocked process is holding and the amount of time process that has for consumed. Selecting a victim, we will roll back to the safe state, restart it from that state. It is difficult to determine which safe state is. Simplest solution is total rollback. You can choose one process at a time and roll back. If you are not sure, it is difficult to implement the safe state after rolling back also, you do the total rollback. Abort the process, then restart it. What happens is when you're choosing some process to terminate, every time you are selecting a process to terminate, the same process is chosen again to terminate again and again based on the cost factors, which may lead that process to starvation. Okay, in the system, when a process is selected to kill based on various factors, the same cost is calculated again and the same process is selected as a victim. As a result, process will never complete its designated task. It will enter into a starvation situation. Practically, we should address. So we can ensure that process can be picked at a victim only finite number of times. Only few times only you should pick. After that, you should allow, although it has cost factor is low, you should allow it for consideration for its execution. Choose some other victim. So this is one way we can recover from the deadlock. Okay, so these are the things that we need to remember about deadlocks. This is exhaustive, but I guess it will make some sense to you. If not, please go through the slides and let me know. This should be 7. Okay, guys, you have any questions? If you have any questions, please ask. Okay, I'll upload the slide. Go through the slides. If you have any doubts, you ask me in the next class. Check your slides whether you're able to see the slide. Lecture 21. Deadlocks is visible.
Yes, sir, it's visible.
Okay. So I'm giving you one assignment for you. Assignment 4. You do that. One is assignment implement CPU scheduling algorithms that we discussed. FCFS, round robin that we discussed, right? Implement CPU scheduling algorithms such as FCFS, shortest job first, shortest remaining first, SRF, SJF, round robin, and priority scheduling. Okay, then 2, implement today's class what we discussed, Banker's algorithm. That is the best algorithm to avoid the deadlock in any language you like. You can implement in C language, you can implement in any language and submit it by next week, Feb 3rd. By Feb 3rd, you submit this assignment. Okay, so this is your 4th assignment. Implement CPU scheduling algorithms. First come, first serve. So you take the arrival time, you take the burst time, you take the number of processes, and calculate the waiting time. Calculate the waiting time and tell me which is the best. What are the examples we discussed? Implement the same. Second, implement Banker's algorithm, because this is the algorithm practically that is used to avoid the deadlock. So if you try to implement, then you will understand how the algorithm is working. Okay, so this is your assignment 4. If you don't have any doubts, we will stop here. We will meet on next Tuesday. You can leave.